Let's now turn to actually constructing covers. And we really know how to do this because we know how the fiber over a point is. So we studied this only over the base point formally. The same argument works over any other point. So here is our example. We have the cylinder covering the torus. We are given a map P. We have a point X naught, and previously we looked at the fiber over X naught, but if I want to look at the fiber over any point X, then I have the base point Y0, and Y is a typical point in the fiber. Okay, then we can do the same thing we did earlier and get a path from Y0 to Y and push it down to paths from X0 to X. Okay. Unfortunately, this doesn't form a loop. So in the case of X0 to X, when X0 was equal to X, that is when we had a loop, we got an element in the fundamental group. But doesn't matter, we have a fiber here and we have X0 and X. Suppose I took a different path, okay, maybe the one which went like this. I still get a loop, which is the difference between these two paths. So let's give them names. Suppose this guy is alpha and the other one is beta. Okay, and then they are lifted up to paths, and perhaps in this case, if the picture is correctly aligned, they actually go to the same point Y, but they may not. So if I have two different paths which are not homotopic, they may or may not go. So this guy lift is beta tilde and the first lift is alpha tilde, where as usual our tilde start at the base point. So what we have is the slight variation of what we had earlier in our description of the fiber. Okay, namely the fiber over X. So suppose we are looking over fiber over X. So what is this? We look at paths, whatever I will call them, alpha from X0 to X. Okay, we had a name for this, so that is omega. So this is divided by some equivalence relation. That is omega of the space X, and go from X0 to X, divided by the equivalence relation. And we know what the equivalence relation is. Previously it was a loop which is alpha wedge alpha star beta bar, okay, belonging to the group H. Okay, so again, as usual, we'll let G be equal to pi 1 of Xx0 and H equals P star of pi 1 of Xx0. Okay, so now you see, if you had the lifts of alpha and beta ending at the same point, then you get a loop here which pushes down to give you the loop alpha star beta bar. Okay, so then it follows that alpha star beta bar is in H. So in other words, we have the relation alpha is related to beta if and only if alpha star beta bar belongs to H. So this is the same description as right cosets, except that alpha and beta are no longer in the fundamental group. Okay, if you think in terms of groupoids, you could think of them as lying in a particular term. But otherwise here we just look at things directly. So this is nice. We know what the fiber over each point X is, and the covering space is just the union of these fibers. Okay, hence we get a description of Y. Okay, so I'll give it a name. We'll call this some other space. We'll call it omega hat of X semicolon X0. Because omega of X0 meant a loop. So this is alpha mapping 0, 1 to X, such that alpha of 1, alpha of 0 is X0. So let's look at all paths starting at various points. They end at starting at X0 and ending at various points. And whatever point it ends at, we'll get the fiber over that point by looking at Y as omega hat, as I called it, of X semicolon X0 by an equivalence relation, where now you have to be a little bit careful. Alpha is equivalent to beta is equivalent to, first of all, they have to have the same endpoint, then they are in the fiber over the same point, and In many programming languages, you'll put an and to emphasize. The second part is defined only if the first part holds. So if alpha of 1 is equal to beta of 1, alpha star beta bar is a loop, and it's a loop based at x naught. So this belongs to H. Okay. So Y consists of fibers. So of course we have P mapping Y to X given by P of alpha is just alpha of 1. By definition, this is well defined because if two things are equivalent, their endpoints are the same. Okay, this is well defined, and also P is surjective. Not always, but it's obvious that this is true if and only if X is path connected. And of course, we are going to assume everything is locally path connected and connected, so this will be true. So here we are nice, and we have also seen from the above P inverse of X is equal to the fiber. I'm sorry. So there's a little bit of a problem. I'll put some decoration over it because I had Y there. Okay. Description of Y given H and H, G and X. Okay, so let me clarify here. The above was a description of Y. So this is a description of Y given only P, H and X. Okay, so this will be the P is going to be given from Y to X, and P inverse X is the correct fiber that we have for the space. So P inverse of X equals the correct fiber. So let me clarify what I mean by this. I mean, if we have an actual covering space, we have associated groups G, H, and we have an actual map P, and we have a corresponding fiber. What we have done is, suppose only X, G and H are data, we have constructed a space Y, but so far only a set Y by using the equivalence relation. And the description is such that as a set it is the same as the original space Y. Okay, and the projection map P of alpha is going to be alpha of 1 is also going to be by this path lifting the same projection map that we had originally. Okay, so remember that we could have points in Y. So if I have alpha, it goes to its certain endpoint, and alpha tilde is its lift. Okay, so the Y is going to be equal to alpha tilde of 1. And the projection of that is going to be alpha of 1. Okay, so here alpha is, I should say class of alpha. Here the class of alpha is the point Y, which is sitting in the fiber. So everything is rather nice here. We have managed to recover a purely algebraic description. Couple of points missing. One is that we have to specify a topology on it, which we will do next, and check when the topology is correct. And then we have to check that this is a covering. Okay, both these cases need hypothesis. Here there is no hypothesis at all for the construction, except if it's not even path connected, then even surjectivity fails. So we'll topologize this. Okay, so we have the space H. This description is following Hatcher. So here we have a point, and we have x0, and we have x. Okay, so topology, recall topology on what? Y is by definition now omega hat of x0 divided by an equivalence relation where alpha is equivalent to beta. Both of these are elements here. If and only if, first of all, alpha 1 equals beta 1. Okay, and so the second condition makes sense, assuming the first holds. This class actually is in H. And notice the data is just G, which is the fundamental group of X, H, so which is contained in G of pi 1 of X, x0. We did not have the space, we constructed it at least as a set. Now we want to give a topology on it. Okay, so we'll define basic open sets. And this is going to be kind of a quotient topology. So let's take an open set U containing X. Okay, so namely let U contained in X be open. And since we want to deal with the path, let us fix one path. Okay, so let's call it gamma, be open, and gamma, so 0 1 is a path from 0 1 to x, gamma of 0 is x0, and gamma of 1 is going to be x. Okay, so then what is the topology here? We look at all little paths over here which are contained completely in U and say that those paths are all in an open set around the original path gamma. Okay, or rather gamma followed by constant. But we don't want it on paths, we want it on equivalence class of paths. If you literally did this on paths, this would be quite badly behaved. So let's define the set Uy as going to be the equivalence class under the appropriate relation we defined just above, gamma star eta, where eta is a path from 0 1 to U and eta of 0 is x. So I look at all such paths and look at them up to equivalence. Okay, why does this contain gamma? That's simple, but it's a good sanity check. So remark the class of gamma is the same as the class of gamma star ex, and so this belongs to U of gamma. Okay, I think I've called that U of y there. That's a mistake. It's U of gamma. Okay, so we have so we have U of gamma here. So we have an open set. So these are defined U of gamma, and U gamma form a basis. For our topology. Okay, in the absence of hypothesis, well, the space would also be different. But if we just have path connectedness but not locally path connectedness, like our famous quasi-circle, which is the guy that comes here and starts oscillating. Okay, so let this point here be x. Okay, and let's take our point x0 here, and let's take a path which is this green color between x0 and x here. Well, you notice that if I took a neighborhood U which sat around this and look at paths within U, I will never reach this side. So the neighborhood is going to be only things on the left. This means that in terms of the topology, this quasi-circle opens up, which is kind of nice in a way. We want it to be regular, but notice it's not even going to be the same space that we started if we sorry, so I should clarify here. Yeah, so it opens up completely. So even if we took G equals H, where we are supposed to be getting a trivial cover, in the absence of all hypothesis, we will not get any the space. So this G equals H is going to be an important sanity check. Okay, but with our SL semi-locally simply connected and locally path connected hypothesis, we will see in the next segment that we actually get the correct topological space and we get a covering.